In chapter 4.2, when we first started studying gradient descent, say on a scalar to scalar function like this one, we saw that the algorithm terminates or converges once it's reached a point where the derivative is really close to zero. The issue is that some functions, like this first example we saw back in 4.2, have local minimums, like this one over here on the right, that aren't the global minimum, so it's possible for gradient descent to get stuck here. This idea of having a local minimum that looks from the perspective of the algorithm like a global minimum isn't unique to scalar functions. We also saw this happening in the more common or the more general vector to scalar case. Remember, we looked at this example in 4.2. Here, depending on where we start the algorithm and what our step size is, we can get caught in one of these two local minimums rather than the global minimum. And remember, the point of gradient descent is to try and computationally identify where the global minimum of a function is, because the kinds of functions we are going to use with gradient descent are empirical risk functions in which the global minimum corresponds to the combination of model parameters that have the smallest mean squared error or mean some other loss function. And that'll give us the best predictions, right? This all has something to do with finding optimal prediction. So what I want to study here is what tells us whether a function is going to have a local minimum in the first place. Okay, that's like broadly the point of this video in chapter 4.3 once it eventually exists. What kinds of functions have local minimums, and when can we guarantee that a function doesn't have a local minimum and we're not going to sometimes get trapped in it? And the big idea in this video is that of convexity. Okay, and you may be familiar with the idea of convexity from Calc 1, where you reasoned about it to see if you found a critical point that is a maximum or a minimum. And that's similar logic that we're going to follow here, but we're going to take a more linear algebraic approach and one that generalizes beyond scalar to scalar functions. Okay, the intuition you should have is that a convex function is one that is bowl-shaped upwards. Okay, the way that I've sometimes explain this is a convex function is one that looks happy. Okay, it's sort of a bowl shaped pointing upwards. But the slightly more linear algebraic approach we're going to take here is a function is convex if it's true that you can pick any 2 points in its domain, say like, I don't know, we take this point x, this point y, and you connect the dots between the function at those 2 points. So this is maybe f of x, and this is f of y. And if f is convex, it's true that whenever you do this for any x and any y in the domain of f, the line connecting f of x and f of y, this is called the secant line. The secant line has to be on or above the function. So notice here, the function is entirely below the secant line. That's good. An example of a non-convex function, I don't know, might be, that example is a little messy, might be something like this, okay? Where here there are plenty of points, x and y, in the domain of the function, where if I connect the line between those 2 points, f of x and f of y, it goes below the function, okay? So intuitively speaking, a function is convex if it's true that you can connect any 2 points on the function, and that line, called the secant line, lies on or above the function. Notice I'm not saying it has to be strictly above. There's a stricter version of convexity called strict convexity that requires that it's entirely above. For now, I'm just saying on or above. And that's this inclusion of the on or above, so the inclusion of the on case allows us to say something like the absolute value function is convex, or even just a line is convex, because in a line, if you connect any 2 points, well, of course it stays on the line, it's just that line, right? An absolute value function over here is also convex using this on or above definition, because sometimes the secant line is above. You pick x's, like an x and a y that are on different branches of the curve, like this one. But if you pick 2 points that are on the same branch, well then that's where the on case is necessary. Okay, so what I want to try and do first is come up with the formal way of stating this definition of convexity. That is, this condition where any 2 points on the graph, when you connect them, the line is always on or above graph. Like, how do I actually state that in mathematical notation? I could just give you the definition, but I think sometimes it's hard to make sense of it when you're given it. And so I'd rather just us derive it from scratch. Okay, so just to have as a running example, I'm going to draw some function. It's not convex, but for this it doesn't really matter. And again, let's suppose this is our x-axis. Note that I'm drawing this example in terms of scalar to scalar functions, but that part is not important here. Everything we are doing is going to translate to vector to scalar functions just perfectly. And what I want to do again is consider 2 points in the domain, x and y. Here's my question. Again, if this is f of x and this is f of y, what is the equation of this line segment? Not of the entire line, like not of this entire line here. I could find that too. But what I really care about is some way to describe just this segment. Okay? And the tool that I'm going to use from earlier in the semester is that of the parametric form of a line, right? And essentially what I'm going to try and describe is this segment as a parameterized line where, say the parameter in my line is t, okay? If t is equal to 0, I want the output of my line to be this point right here, like x comma f of x. And if t is equal to 1, I want my point to be here, y comma f of y. And if t is somewhere between 0 and 1, we're looking at a point somewhere between f of x and f of y. So you can think of t as being like the percentage of the way we are between the starting end point of the line segment and the ending point of the line segment. So again, t equals 0 should start here, and t equals 1 should start here. Okay? First, I'm going to try and describe this line, and then I'm going to try and describe the condition where for any of those t's, the place we are on the line must be above the corresponding point on the curve. So for example, this point here roughly will correspond to, I don't know, t equals 0.7 or something like that, because we're 70% of the way between x and y. My condition is going to say this point must be greater than or equal to this point. Okay, and if I extend that to all possible t's between 0 and 1, well then it'll extend this sort of condition to any point underneath the line segment here. Okay, so taking a step back, I know this is getting a little messy. What I'm trying to do is figure out a way to parametrically describe this line segment. And what I was just explaining is why that parametric definition would be useful. Okay, so how would we do it? Well, here is a starting point on the line, and here's an ending point on the line, and the change between them is just their difference, f of y minus f of x. So one way to try and describe this line segment is perhaps as something like f of x, and I'll say L is f of x plus t times the difference of f of y minus f of x, where again t is somewhere between 0 and 1. It could be exactly 0 or exactly 1. This parametric description matches the intuitive sort of introduction I gave earlier, where if t is equal to 0, well then you don't look at this and your output is just f of x. And if t is equal to 1, well then you have f of x plus 1 f of y minus 1 f of x, and then the f of x's go away and you're left with just f of y. Okay, so this looks like a parametric version of the line segment. Though, for reasons that will become clear in just a little bit, I'm going to expand out this t, this parentheses at the end, and write this as f of x plus t f of y minus t f of x. okay? And if I collect like terms here, you'll see that this is equivalent to 1 minus t f of x plus t f of y, okay? This is an equivalent form of the same parameterized line segment. All I did was just some algebra to go from here to here. Now, typically, when you see other textbooks give you the definition of convexity, it'll start by using something of this form, and you just kind of have to take the leap of faith that this has something to do with the line segment. But I'd rather start with this slightly more intuitive way of looking at it and then build up to this. But here, this form also provides us with a little bit of intuition, because you can see, again, if you say t is equal to 0, then your output is just f of x. If t is equal to 1, well, then 1 minus 1 turns this piece off, and you're left with just f of y. And if t is somewhere in between, like if t is 0.2, well, then you're taking 20% of y's output and 80% of x output. So you're like gradually changing which weighted combination of f of x and f of y you want, and that gradual change is reflected by this line segment. Okay, so this parameterized line is describing this segment, okay? And again, what I'm trying to put in mathematical terms is a statement that for any t between 0 and 1, and of course for any x and y in the domain of the function, whatever this thing spits out has to be higher than whatever the curve spits out directly below the line, okay? And so what we've described now is the coordinates of this point for any x, y, and t. What I need to describe now are the coordinates of this point, okay? And hopefully it's not that much of a stretch to call this point here f, right? It's something on the function, so it's going to be f of something. I want to call this f of 1 minus tx plus ty. Now is a good point, now is a good opportunity for you to pause the video and think about why the y, using too many of the same terms here, but think about why the output of the function at this point that I'm circling is f of 1 minus t times x plus t times y. Why does that make sense? Now's a good time to pause the video and think about it. But once you've thought about it, I can try and make it a little more clear. Right here, this segment, which is parameterized by, or which is described by this expression, sweeps from f of x to f of y gradually as t goes from 0 to 1. Similarly, if you look at just the piece within here, the 1 minus tx plus ty, that sweeps similarly from x to y. All I did was replace f of x and f of y with just x and y here. So if t is equal to 0, this thing outputs x, and if t is equal to 1, this thing outputs y, and if t is somewhere between 0 and 1, this is going to be somewhere between x and y, okay? And now all I'm doing is I'm taking that sweeped, or like that sum point between x and y, and remember x and y are just two inputs to the function, and I'm passing that thing between x and y, here it would be a number, but in general it would be a vector as well, I'm passing that into the function. And all I'm saying is that for any x, y, and t, where x and y are just points in the domain, and t is somewhere between 0 and 1, this thing, that is the point on the line segment, needs to be higher or equal to the point on the function. And so all I've described here, rather, let me say it this way, convexity, all it is what I've just described here, okay? If you connect any 2 points on a graph and draw the line segment between them, that segment needs to be on or above the curve. And all I've tried to do here is give us a more precise way of stating that definition. And so now we have all of the pieces in the definition. Let's actually state it. So we'll say convexity. F, and in general, this definition extends to vector to scalar functions as well. So I'm going to give you that super general definition. F, and this is a vector to scalar function, it takes in d input variables and spits out just one input variable, is convex if and only if, but I'll start just by saying for all x and y in Rd and all t between 0 and 1, and I'll write it slightly differently just to give you another way of thinking about it. For all t between 0 and 1, the line segment is greater than or equal to the function. What expression on the previous slide described the line segment? It was this one, right? 1 minus tf of x plus tf of y. So I'll put that here. 1 minus tf of x plus tf of y. That thing is greater than or equal to the function of 1 minus tx plus ty. This right here is the formal definition of convexity. Okay? Now, I should have fixed one thing before highlighting, which is that I'm claiming that this is the definition for vector to scalar functions, but in here everything is a scalar. The things that need to be vectors are x and y. There we go. But if x and y are vectors, and so they're vectors in R7 or R15 or just RD in general, this piece is still the parameterized line between f of x and f of y, and this piece inside here is still the parameterized line between x and y, and all I'm doing is plugging that point between x and y into the function, and I'm saying function needs to be less than or equal to line segment between those points. Okay, so again, this is the formal definition of convexity. Okay, so now that we have this formal definition of convexity, what can we actually do with it? What I'd like to do is show how we can use this formal definition to prove relevant facts about the kinds of functions we would use gradient descent to minimize. Remember, all of this has something to do with gradient descent and giving us some assurances that we're not going to get trapped in local minimums when running gradient descent, or at least telling us in advance that it's a possibility to get trapped in a local minimum. Okay, and the first fact I'd like us to prove is that if f is convex, then any of its local minimums are global. Meaning, if f is convex, just using this definition, we can rule out a possibility like this one, where there's a local minimum that is not the global minimum. Okay, and so what I'm going to try and prove is that if f, and we'll consider the general vector to scalar case, is convex, then any local minimum is a global minimum. Okay, and what I'm hopefully illustrating in this proof, the way I do it, is how to use the formal definition to get out of it useful results. Okay, and I'm gonna do one or two examples of this with you here, but then in lab and in the mock exam and the real exam and in homework 9, you're gonna work through similar examples of using the formal definition to spit back out something we want. Okay, so the way that I'm gonna approach this argument is by contradiction. And it's okay if you haven't taken EECS 203. If you have, this idea will be familiar. But essentially, the way that a proof by contradiction works is we start by assuming that this is not the case. And then if this is not the case, then something nonsensical happens. Meaning that the initial thing we assumed, that is, this being wrong, had to itself be wrong, meaning this has to be true. Okay? And so let's start by contradiction. Let's assume, I don't know, x star is a local minimum, but I don't know, z is a global minimum. And remember, I'm writing these as vectors because in general, f takes in vectors, not just scalars. Okay? And actually, we don't even need to assume that z is a global minimum, but assume that f of z is less than f of x star, meaning that x star is a local minimizer, but it doesn't have the lowest function output possible. So the intuition to have is that, again, we're dealing with something like this, where this point here would be x star comma f of x star, and z is just anything with an output lower than this one. So like this could be z f of z or something. Okay, let's assume that this is the case. What I'm going to do, and you'll see this happening in a lot of these formal definition of convexity proofs, is just plug in x star and z into the formal definition of convexity. So let's see what the plugging in x star and z into the definition from the previous slide gives us. Okay, because remember, this definition works for any two inputs to the function x and y. It doesn't matter what these are, as long as they're valid inputs to the function. I can use this definition of convexity, and remember, t can be anything between 0 and 1. What this states is that function, so f of 1 minus t x star plus t z is less than or equal to 1 minus t f of x star plus t f of z. Okay, and remember, the left-hand side, that is the thing that is smaller in the definition of convexity, is the one where the function is wrapping the entire thing, because the whole point is that the function, if the function is convex, which this one, of course, isn't, the function is below the line segment. So this is the line segment, this is the function. Okay, what does this tell us? Well, we know, really all we know, based off of the setup of our proof by contradiction, is that f of z is less than f of x star. Okay? And so what does that tell us? It tells us that this piece here, and I know it's kind of hidden, this piece, f of z, is less than f of x star, right? So this entire expression itself is less than whatever it would be if I plugged in f of x star here instead of fz, okay? And I know it would be slightly more intuitive if I was writing this to the right of this rather than beneath it. And I know like the space is a little compressed, but the intuition, I mean, the math is the same, right? By the assumptions of our problem setup, this number is less than f of x star. So this entire thing should be less than whatever it would be if I plug in f of x star here. So let me do that. All of this is less than whatever I would have if I had 1 minus t f of x star plus t of f of x star again. Okay, but now all I have going on here are f of x stars, right? There's no more f of z's. So if I expand this out, this just gives me f of x star minus t f of x star plus t f of x star. And here, the t f of x stars go away, and this is really just f of x star. Now, what is the issue with what we've just stated? Because the contradiction itself isn't immediately obvious. Let me rewrite in the next slide slightly more clearly the final result of this expression. But notice we've turned this less than or equal to into a strict less than because of this assumption that f of z was less than f of x star. The conclusion from this slide was that f of 1 minus t x star plus t z is strictly less than f of x star. Why is this a contradiction? That part may not be immediately obvious. But what this is saying is some f, let me start by motivating it this way. What would happen if I plug in t equals 0 into this? Well, if I plug in t equals 0, it zeroes out the x the z piece in this weighted average, and I just have 1 minus 0 times x star, this would tell me that f of x star is less than f of x star. That would be a contradiction. But even if you didn't immediately jump to plugging in t equals 0, what else would this tell me? If I plugged in t equals 0.001, what this would give me is some point, some input that is really close to x star, but not exactly the same as x star. It's like x star plus a little bit in the direction between z and x star, right? So if I plug in t equals 0.001, this is going to give me something that is not x star, but it's really close to x star. And this would be saying that the f near x star is less than f of x star. And hopefully now this is making the contradiction a little more clear. Remember, the initial assumption that it was that x star is a local minimizer of f, which meant that in some neighborhood around x star, f of x star was the smallest possible value. But what this is saying is that you can make t as small as you want it to be. You can be like immediately next to x star, and this f is still less than f of x star, which contradicts the assumption that f of x star was the minimum point in some neighborhood. This is saying, hey, no neighborhood like that exists. I can pick a point that's infinitesimally close to f of x star, and it's still going to be less than it. So this is actually not a local minimizer, which is the contradiction. But again, the easier way to see the contradiction is just plug in t equals 0, and then on the left you get f of x star, and on the right you have f of x star, and of course, box cannot be less than box. And there's your contradiction again. So going back here, we assumed that x was a local minimizer, but that it wasn't the global, meaning that there was some other point that was less than it, just not in its neighborhood. And that assumption has led to something nonsensical, which means that assumption, that is that x star was a local minimizer but not global, is not true, which means that any local minimizer is indeed a global minimizer. Okay, so this formal definition of convexity has ruled out cases like this, where if we have a local minimizer, then it isn't possible to have some global minimizer that is lower than it, so that if we have a local minimizer, it is also the global minimizer. That's important because it tells us that if a function satisfies this vague-looking condition, then gradient descent should be well behaved on it. It's not going to get trapped in some local minimum. Now here's another question. Not a proof, but a question. Do all convex functions have a global minimum? Think about it for a second. You can pause the video if you would like. The answer is no. Okay. A simple counterexample is like a line, right? This is perfectly convex. It satisfies the condition that if you pick any 2 points on it, that this line segment is on or above the curve. It'll just always be on it. And a line doesn't have a global or local max or min, right? It tends to infinity in both directions. So the answer is no. But there's a slightly stronger version of convexity called strict convexity, and I'll state that here because the final example we will work with involves it. Strict convexity. And that states that you can't have the equal to case. It states that the function is always, don't need the parentheses there, is always strictly less than the line segment. And the equal to case is not there. So for example, this function, and this is again for all x and y in the domain and t between 0 and 1. This is strict convexity. And so like an example of a function that is convex but not strictly convex is this one. Because sometimes when you connect 2 points, the segment is above, but sometimes it's just on. So this is convex but not strictly convex. And we'll get back to that idea in a second. But there are some functions that are strictly convex and also don't have a global minimum. And if you haven't thought of an example, here's one. The function f of x equals e to the x, for example. This doesn't actually have a global minimum. That is, there's no one number that you can state that is an output of the function and is less than every other output of the function. That's what a global minimum would be. Now, you might say the global minimum of this is 0. And it's true that as x gets smaller and smaller and smaller, that is, as x approaches negative infinity, f of x approaches 0. But 0 is not a global minimum of e to the x because there's no input to f that gives you 0 as an output. Like no x makes f of x equal to 0, which means it's not a global minimum because it's not a possible output of f. But this function is perfectly convex, right? Proving that it's convex using the formal definition would be a little difficult, though doable. It's the second derivative test that would be slightly more useful here. But again, the utility of our formal definition is that you don't need the second derivative test because you don't need the function to be differentiable. You can use it on things like this. Anyways, this is a perfectly convex function. It's strictly convex as well, but it doesn't have a global minimum. It approaches a value, but that value it approaches is not one of the outputs of the function. So it's not the case that all convex functions have a global minimum, which is why the thing we proved over here was that if it has a local minimum, then that thing is also a global minimum. But it's not saying that every convex function has a global minimum. Important subtlety. The last thing I wanted us to prove together is involving strict convexity. If a function is strictly convex, I want us to prove that it has a single unique minimum. Okay? Now, it may seem like we've already proved that, right? It seems like back here, we proved that if a function has a local minimizer, then that minimizer is also a global one. But here's a case that perhaps you thought of, but I didn't initially think of when I was reasoning about convexity, and it's a function like, I don't know, this one. And we saw functions like this back at the start of the semester when we learned about mean absolute error, for example. This function is convex. It's not strictly convex. And it's true that any local minimum is a global minimum. It's just that there isn't a unique local minimum. There's like a flat valley, right? And you can imagine this extending into multiple dimensions as well. Local min equals global min. But multiple, sorry, that's messy, minimizers. Right? There's plenty, of x's and y's and z's that all can claim to be the local and global minimizer because of this flat valley. Now, of course, this function is not strictly convex because if there's plenty of places where I can connect 2 points on the line, on the graph, connect the line and the line is not above. For strict convexity, we need it to be strictly above. For just convexity, on or above is okay. And so what I want to prove, and that'll be the last thing we do here in this video, is that if f is strictly convex, then its global minimum, if it exists, is unique. Okay, and again, now is a good point to perhaps pause the video and think about how you would go about proving this. But here's what I want to try and do. And you'll see that we're going to approach this similarly in some ways to the first proof we did involving the definition, which is that any local minimum is a global minimum. Suppose this is not true. So again, we're going to do this by contradiction. Suppose x star and y star are different vectors, but both minimize f, or are both global minimizers of f. i.e., f of x star equals f of y star, and let's call it minimum output m. Okay, so again, I'm trying to prove that if f is strictly convex, then if it has a global minimum, that's unique. Like there's only one x or one input that describes that minimum possible output. So we're going to start by contradiction, and we're going to assume, hey, let's suppose that's not the case, and let's suppose f is strictly convex, but its global minimum isn't unique. Okay, and so let's say there are two of them, x star and y star. Again, in these sorts of proofs, you want to state your assumptions clearly and then use the formal definition of convexity and see what it tells you about the situation, right? And so I'm going to plug in x star and y star into that formal definition. Remember, f of a lot of stuff, that is f of something, is on the left because function is less than line segment. This could tell me f of 1 minus t x star plus t y star is less than, remember here's where the strict part is important, 1 minus t f of x star plus t f of y star. Okay, but remember here f of x star and f of y star are the same thing, so this is 1 minus t f of x star, which is m, plus t f of y star, which is also m. Make it more clear that this is addition. But 1 minus t times m plus t times m, we've seen this already. This is just the same thing as m. Where's the contradiction? Well, now what this is saying is there's some other input to the function that gives you an output that is less than m, right? This is saying f of something is less, strictly less than m. But remember, the assumption was that x star and y star both are global minimizers of f, meaning that there's no other, like there is no possible input to the function that gives you an output that is less than m. M is the bottom of the function. But what this is saying is that if f is strictly convex, and you assume it has multiple minimizers, that is multiple inputs that give you that output of m, well then there's a contradiction, because if that were true, then there would be some input between x and y, or x star and y star, that gets you lower than m, which is not possible because m is assumed to be the global minimizer. So there's your contradiction, which means that the thing we just assumed was wrong, and we assumed that it's possible for x star and y star to exist, be different, but both be global minimizers of f. And so the thing that's wrong is that they're both global minimizers of f. And so it's true what we are trying to prove. That is, if f is strictly convex, then its global minimizer, if it exists, is unique. That is true. And that gives us another way, or another lens of looking at functions that we may use gradient descent on. If we have some guarantee that our function is strictly convex, then we know that there's only one possible x star that minimizes the function. Okay, so like one way to tie some of the ideas that we've looked at recently together is to think about how all of this applies to the mean squared error of a multiple linear regression model. Okay, and I don't want to say too much about this because this is an important idea that I want you to think about on your own here. But can you think of an example where, or an example or a scenario where R is not strictly convex, but is convex? I should start by saying this R is always convex. I'm not going to prove that here. That proof is slightly more involved, and it involves, as I mentioned earlier, extending what we've discussed here into some sort of second derivative test, which is not super straightforward in the case of vector to scalar functions, because there are multiple second derivatives now. If you have 10 input variables, you have 100 second derivatives or second partial derivatives. So I'm not going to do that in this video. I'll just believe me for now that this function is convex no matter what your y's and x's are, but it's not always strictly convex. And so what I want you to think of is a setting in which this is convex, it always is, but not strictly convex. Okay, and think about how this relates to the ideas of optimal parameter vectors and pictures that perhaps look like this one. Like, are there potentially multiple minimizers of mean squared error, and what characteristic is true about all of them? Okay. That's where I think we'll end this video here. The point of this video, again, was to give you some intuition for the formal definition of convexity, which you're playing around with in this week's materials and can show up on the exam. Thanks for watching.